Hello, Matt here from chemistrystudent.com. In this video, we're going to look at the electrophilic addition reaction between an alkene and concentrated sulfuric acid. We're going to talk about why and how this reaction happens, outline the reaction mechanism, and look at how we can predict the major and minor products of such reactions with unsymmetrical alkenes. Before we talk in detail about the reaction, there are a few essential ideas you need to be comfortable with. Alkenes are unsaturated hydrocarbons that have a carbon-carbon double bond in their carbon chain. The carbon-carbon double bond is made up of a sigma bond and pi bond, with the pi bond being weaker than the sigma bond. This weaker pi bond is quite easy to break, as it has a low bond enthalpy, and this gives alkenes a relatively high reactivity. Electrophiles are electron pair acceptors. They are attracted to areas of high electron density and are electron deficient, often with a positive charge. A carbon-carbon double bond is a region of high electron density, and electrophiles are attracted to this area in a molecule, making alkenes susceptible to electrophilic attack. Nucleophiles would be repelled by this high electron density, and this is why alkenes react with electrophiles rather than nucleophiles. And the alkenes react by electrophilic addition reactions. An electrophile accepts a pair of pi bonding electrons from the carbon-carbon double bond in the alkene, forming a new bond to one of the carbon atoms, and leaving the other carbon atom with a positive charge, forming a carbocation intermediate. The positively charged carbon in the carbocation will then form a new bond with a negatively charged ion. This ion is usually produced as the electrophile gets formed. Addition reactions occur when groups or atoms are added to a molecule, forming only one product. In organic chemistry, we showed the possible steps occurring in a reaction by using mechanisms. Curly arrows are used to show how a pair of electrons move to break and form bonds. The arrowheads always point towards where the electron pair is moving to. A carbocation is an ion that contains a carbon atom with a positive charge. Carbocations can be primary, secondary, or tertiary. For primary carbocations, the positively charged carbon is bonded to one other carbon group. For secondary carbocations, the positively charged carbon is bonded to two other carbon groups. And for tertiary carbocations, the positively charged carbon is bonded to three other carbon groups. Recap done? Let's go! When an alkene reacts with concentrated sulfuric acid, an alkyl hydrogen sulfate is formed. The reaction happens easily and can be carried out in cold conditions. To get any reaction started with an alkene, we need to have an electrophile. Now, if we look at the structure of sulfuric acid, H2SO4, we can see that the hydrogen atoms in each molecule have a very large partial positive charge, making them electron deficient, and this enables them to act as an electrophile. As a sulfuric acid molecule approaches the carbon-carbon double bond in an alkene, the electron-deficient hydrogen atom in the acid accepts a pair of pi bonding electrons from the double bond. This breaks open the double bond, and a single sigma bond is still left between the two carbon atoms, meaning the carbon chain doesn't get broken. As this happens, the electrons in the bond between the hydrogen and the rest of the sulfuric acid will break, leaving a negatively charged hydrogen sulfate ion behind, with the oxygen previously bonded to the hydrogen getting a new lone pair of electrons. The reaction now just proceeds as expected for an alkene. An unstable carbocation intermediate is formed with a carbon atom that has a positive charge. The negatively charged hydrogen sulfate ion will get attracted to the positively charged carbon in this intermediate, and the oxygen with the new lone pair of electrons will form a bond with it, completing the addition reaction and forming the alkyl hydrogen sulfate. If you are at all unsure about this standard mechanism, please check the links in the description below for other videos about the electrophilic addition reactions of alkenes and their mechanisms. Let's have a quick recap of this mechanism using ethene and sulfuric acid as an example. A sulfuric acid molecule gets close to the carbon-carbon double bond in ethene, and an electron-deficient hydrogen atom, with a partial positive charge, acts as an electrophile and accepts the pi bonding electrons from the double bond. A new bond gets formed between one of the double bonded carbon atoms and the hydrogen. This forces the carbon-carbon double bond to break, with the other carbon atom ending up with a positive charge, forming an unstable carbocation intermediate. Whilst this happens, the bond between the hydrogen and the rest of the sulfuric acid molecule also breaks, giving the oxygen the hydrogen was bonded to a new lone pair of electrons and forming a negatively charged hydrogen sulfate ion. The negatively charged hydrogen sulfate ion gets attracted to the positively charged carbon in the carbocation intermediate, and the oxygen with the new lone pair of electrons forms a bond to it. This creates a new molecule, an alkyl hydrogen sulfate, called ethyl hydrogen sulfate. The ethyl comes from the fact a 2-carbon alkyl chain is bonded to something, and the hydrogen sulfate tells us that this is what the ethyl chain is bonded to. As an extra note here, water could then be added to this ethyl hydrogen sulfate to form ethanol, CH3CH2OH, and reform sulfuric acid. If the alkene reacting with sulfuric acid is unsymmetrical, there can be two possible products that may be formed, with one, called the major product, more likely to form than the other, the minor product. This has been covered in much more detail in a separate video about the electrophilic addition of alkenes with hydrogen halides. If unsure about it, please check the link in the description below. In simple terms, the hydrogen from sulfuric acid is more likely to bond to the carbon in the double bond that is bonded to the fewest other carbon atoms. This will mean the positive charge in the carbocation intermediate ends up on the carbon bonded to the most other carbon atoms. This is because of the positive inductive effect of carbon groups. This positive inductive effect describes the ability of a carbon group to push electron density towards a positively charged carbon. This effectively reduces the amount of positive charge on the carbon as electrons are negatively charged, and this stabilizes the carbocation ion. It enables the positive charge to be spread out through the ion rather than being forced to be localized on one carbon atom. For example, with propene and sulfuric acid, the hydrogen from the acid molecule can bond to either of the carbons from the double bond. If it bonds to the first carbon, carbon 1 here, a secondary carbocation intermediate will form, and the positively charged carbon atom is bonded to 2 other carbon atom groups. If, however, the hydrogen bonded to the second carbon, carbon 2, a primary carbocation intermediate will form, and the positively charged carbon atom ends up bonded to only one other carbon atom. 2 carbon groups gives a greater positive inductive effect and stabilizes the secondary carbocation more than the single carbon group can in the primary carbocation, making the secondary carbocation intermediate more likely to form. This means the hydrogen sulfate group is more likely to end up on the second carbon, making this the major product. Both structures will end up forming, just more of this major product will form compared to the other minor product. As I said, this has been explained in much more detail in the video about alkenes reacting with hydrogen halides. Link in the description below. So, to summarize, alkenes react with electrophiles in electrophilic addition reactions. Electrophiles, electron pair acceptors, are attracted to the high electron density in a carbon-carbon double bond. When an alkene reacts with cold concentrated sulfuric acid, an alkyl hydrogen sulfate is formed. A hydrogen with a partial positive charge from the acid molecule is electron deficient and able to act as an electrophile. It accepts a pair of pi bonding electrons from the carbon-carbon double bond in the alkene, and this forms a new bond between the hydrogen and a carbon atom, leaving the other carbon atom from the double bond with a positive charge, forming a carbocation intermediate. A single sigma bond still remains between the two carbon atoms. At the same time, the bond between the hydrogen and rest of the acid molecule breaks, giving the oxygen the hydrogen was bonded to a new lone pair of electrons and forming a negatively charged hydrogen sulfate ion. The oxygen with this new lone pair of electrons in the hydrogen sulfate ion will make a new bond with the positively charged carbon in the unstable carbocation intermediate, and an alkyl hydrogen sulfate is formed. The reaction is an example of electrophilic addition, as the reaction is started by a hydrogen from the acid acting as an electrophile, and only one product is formed, with a hydrogen and hydrogen sulfate ion getting added to the alkene, making this an addition reaction. If the alkene reacting with sulfuric acid is unsymmetrical, there may be two possible structures that can be formed, giving a major and minor product. The hydrogen from the acid is more likely to bond with the carbon in the double bond that is bonded to the least number of other carbon atoms. This is due to the positive inductive effect of carbon groups stabilizing the carbon with a positive charge in the intermediate, making secondary and tertiary carbocations more likely to form than primary carbocations. I hope you found this video useful. Please check out other relevant videos in the links given in the description below, and visit chemistrystudent.com for free notes and revision materials.